Hi everyone, welcome to Lesson 19, Ultrasonic Rangefinder Introduction. So in this lesson you'll learn what sound is and how sound pressure is detected, what frequencies comprise the ultrasonic frequency range, components of an ultrasonic rangefinder, how a piezoelectric transducer works, an overview of ultrasonic sensor electronics, and some applications of ultrasonic rangefinders. Now we can define sound as a mechanical wave that results from the back and forth motion of particles of a medium through which the sound wave is moving. Now sound will generally propagate as a longitudinal wave in a fluid, such as air, and the particles in this longitudinal wave will oscillate back and forth in a direction that's parallel to the direction the wave is moving. Now the particles always return to their original position, and it's only the energy that's actually transferred. So to actually make sound, we need a vibrating source. And in the figure, if we take the example of a tuning fork and we strike it, this vibrating source then is going to create regions in the medium where the particles are either squeezed, and we call these compressions, or in other regions where the particles are actually spread apart, and we call these rarefactions. Now in the compressed regions, they're areas of high pressure, and the rarefaction regions are areas of low pressure. So if you use a detector such as a microphone, it will detect the fluctuations in air pressure, and we would take these fluctuations, convert them into electrical signals, and then process them. Now the human ear frequency sensitivity is from about 20 Hz to 20 kHz. And ultrasonic refers to frequencies greater than the audible range, and it can actually extend into the gigahertz. Now bats and certain marine mammals will use echolocation, and so they communicate and navigate using ultrasonic frequencies, and this is from about 20 kHz to 100 kHz. Now medical ultrasound diagnostic equipment operates much higher at a range of about 2 to 15 MHz. Now a typical ultrasonic sensor will be composed of one or more ultrasonic transducers and processing electronics. And how it works is a series of pulses will be sent from the sensor, and if there's an object within the sensor's range that is in front of the sensor, a fraction of the pulse will echo back from the object to the sensor. Now that echo is then converted to an electrical signal, and it'll be processed by sensor electronics. And the sensor will output an electrical signal with a pulse width that's directly proportional to the distance to the object. So two common technologies for ultrasonic transducers include magnetostrictive and piezoelectric. In this course we'll talk about the piezoelectric type. So the piezoelectric type utilizes the piezoelectric effect whereby positive and negative charges in a crystalline material will accumulate on electrodes on opposite sides of the material, and this is in response to mechanical stress. So this is either stretching or compressing. Now an electric dipole is created when the piezoelectric material is deformed. If we take a simplified example for quartz, you can see that quartz is made of silicon with a positive charge and oxygen with a negative charge. So on the figure on the left, there's no electric dipole because the charges are balanced. Now if the material is compressed, you can see that there's more silicon atoms towards the top of the material and more oxygen atoms towards the bottom of the material. So there's a net positive on top and a net negative on the bottom. The opposite is true for tension. What's left is an oxygen atom at the top producing a negative charge and a silicon atom towards the bottom. So the top of the material has a net negative charge, and the bottom of the material has a net positive charge. So the voltage polarity measured is going to be dependent on how the material was manufactured. So in the figures to the right, tension is going to produce a negative voltage when measured as shown, and compression will produce a positive voltage when measured as shown. Now if you alternate compression and tension, you're going to generate an alternating voltage. So for the inverse piezoelectric effect, the application of an electric field is going to create mechanical stress, and this is going to distort the original shape of the material. Now in the figure, the application of negative voltage causes the material to elongate in the horizontal direction, and the application of a positive voltage causes the material to compress in the horizontal direction. Now the application of AC voltage is going to cause the material to oscillate at whatever the applied frequency is. So the ultrasonic transducers are typically made of piezoelectric ceramics, and common ones include barium titanate, lead titanate, and lead zirconate titanate. The ultrasonic transducer consists of a piezoelectric element that converts an applied electrical signal into a mechanical vibration that oscillates at a particular frequency. So this same element, or a second element, in parallel will receive the reflected pulse and it will deform, and this generates an electrical signal that's read by sensor electronics. So the transducer consists of a case, and within that case there's epoxy potting, a backing material, the piezoelectric element, and a wear plate. Now the epoxy minimizes vibration and it holds all the components in place. The backing material is used for support and it will attenuate any acoustical signal that radiates into the back of the transducer. The wear plate or protective cover actually protects the piezoelectric element, and the device is constructed to maximize resonance at a particular frequency and to minimize any acoustic mismatch. The ultrasonic sensor can be found in one of two configurations. In the first configuration, there's a single transducer. This generates the sound pulse, and it also receives the echo. An example of this is the Maxbotic sensor shown at the top right. The other type of sensor consists of two transducers that are placed next to each other. So one's going to generate the sound pulse, and the other transducer is going to receive the echo. And our parallax ping sensor is of this type. The ultrasonic sensor electronics consist of a transmitter section and a receiver section. And at the heart of this is a microcontroller. Now, for the transmitter section, the microcontroller is going to output a series of square wave pulses. Typically this is at 40 kilohertz, and that signal is fed into the ultrasonic transmitter, converted to sound, and the sound is output in front of the sensor. Now, if there's an object that's within range of the sensor, a fraction of that sound is going to be reflected and will be received by the ultrasonic receiver. Now, that signal has been attenuated quite a bit, so it needs to be amplified, and it also needs to be filtered to remove noise. After that amplification and filtering, it's fed into a peak detector circuit or a comparator circuit, and then it's fed into the analog to digital converter of the microcontroller. Now, at that point, there's generally some code written in the microcontroller to output a pulse that corresponds to the distance to the object. Ultrasonic sensors are used in a wide variety of applications, and to highlight a few, these include diagnostic medical imaging, robot navigation, and even flaw detection in materials. So that's all for this lesson. Thanks for watching, and we'll see you in the next one.